Thanks for the nice introduction. Good afternoon, everyone. My name is Chunyuan. Today I'll describe LOVEU, which is an open source project aiming to build the large multimodal models. So today I'll divide the talk into three parts. First of all, I'll introduce the overall topic, which I call the computer vision in the world, which is actually an ongoing workshop in another building of this year's CVPR. I'll talk about this actually motivated us why we start to build the LOVEU. And moving to the second part, I'll talk about the very first version of LOVEU, where I'll show you how to construct data, how to build a model, and how to evaluate the model for LOVEU or GPT-4-like models. In the last part, I'll introduce the recent advances that we have developed for the LOVEU family. And this includes LOVEU 1.5 and LOVEU Next, and the new variants built on top of LOVEU Next. Let's take a look at the first part. What is computer vision about? The story begins back in 2020, when Microsoft decided to build its own vision foundation models. And we were asking the question, why we want to build these vision foundation models. And in the research community, and we come up this definition that the goal to build a vision foundation model is actually trying to achieve computer vision in the world, or CV in the world, which means that we want to build one model. This model, once the model is built, and we hope the model is able to finish all the vision tasks in the model. And this can be finished easily without further tuning of domain-specific data. And now the pipeline quickly converged. This follows this pre-training and probably fine-tuning or adaptation procedure. It means that we train the large model on the large amounts of raw multimodal models data. And once the model is trained, and we hope the model can complete thousands of tasks in the world. So I summarize the definition of CV in the world. And here I also show the workshop, the GitHub link and YouTube link, where you can check out the more details. So I just want to emphasize two things. One is once the model is built, and we hope the model is able to complete all variance tasks in the world, which means that task transfer scenario are broad. Second one is the task transfer cost is low. Now, I think at this moment, I can use the example of GPT-4V or GPT-4 as example to show you what it looks like when we achieve computer vision in the world, right? And when you play with the interface or playground of GPT-4V, where after you upload your image or video and ask anything about this image or video, and the model is able to provide some decent answers. I think this is the beginning of computer vision in the world. This is cool, but in the research community, we are asking the question, how can we use the resources that are available to us to build such models? And this motivates us to build a LOVEU, in which I view it as the first open source project trying to replicate some of the GPT-4V capability. Let's talk about the LOVEU 1.0 first. So the story, I think, we most borrow it from the language domain. In language domain, so to construct the training data for ChatGPT or instruction to the language model, and it is important to have the diverse high-quality data. And the framework that has been used in the language domain is called self-instruct, where the humans created several examples, including the instruction and its corresponding responses and answers. And we will use this as examples. And we will allow with a property called in-class learning of LLM, and then generate a more diverse set of instruction founding data in the language domain. And this idea has been widely used to build open source language models for instruction following. In the multimodal space, and we trying to borrow the same idea, but it immediately comes to a question that there's a gap. We see that the teacher model is the language model, right, where it can only take sequence or text sequence, while for our student model, which is image language model, where we do need the model to understand the image in some sense. And this is a unique challenge when we build the data for LAVA training. So how we solve this problem? So instead of representing the image using pixels, we will use its symbolic representations. More specifically, we are using captions and bounding box to represent the original image. If you are familiar with this concept, of course, I think you are familiar in this CVPR community, right? Captions, especially in the Coco caption. So there are 5 captions for each images in Coco, and each caption describes the image content from different perspectives. And for a bounding box, it comes with two types of information. One is a bounding box location itself, which is represented using coordinates, and it represents where the object is and how big the object is. And it has another information, which is a concept located in this specific location, right, which is represented using word or phrase. And combine these two, we believe the bounding box highlights the most important objects in the image. So it means that we can represent the image using caption and bounding box, even though this is not perfect, but we believe that it has already approximate the original image in a large degree. Okay, by feeding this sync representation into a self-instruct framework, and now we generate our multimodal instruction following data. And specifically, we are considering 3 types of instruction following data. The first one is a multi-tune QA. And so basically, it asks the question, what are the objects in the image? And what are the attributes? Those are basic questions to describe the image content. And second type of instruction following data, we call it a detailed caption, which is trying to describe the image as detailed as possible. You may imagine there will be a long sequence which can try to describe every single patch of the original image. And last one, we call it complex reasoning. So for this type of instruction, it's not about the content of the original image. It's more about the implications from the original image. Using this example, so we see that there is a small SUV and there are several large luggages on the ground, right? The implication here, or the reasoning problem here is what is the unique challenge for the people in this image? So the challenge is how to put those luggages into the small SUV. So I have introduced the data to train LAVA. Now I'm going to tell you how we construct the model and how we train the model. So in terms of architecture, LAVA is probably the simplest design for any LMM, right? So we start with 2 pre-trained models. One is the vision encoder from Clip, and the other one is Vicuna 1 year ago, which hello. Test. Let me look very good. Thank you. So we use a 2 pre-trained model, the Clip encoder and the language model. So those 2 are pre-trained, which means that a large amount of knowledge has been stored in the model weights. And then we introduce a simple collection module, which is implemented using a linear matrix. and which we call it a projection module in this plot. So you can see that the only trainable module that we introduce to this system is this linear matrix, and which is trying to connect the vision part and the language part. So now let's talk about the training strategy. We consider two-stage training strategy. In stage one, we freeze the entire model weights. We only train this linear matrix using the standard image caption training objective, and this is the train on a subset of CC3 media. And after this stage is done, and we know that the image encoders now is well aligned with the word embedding space of the LLM. And so we call this stage vision language feature alignment. For the second stage, and now this is really visual instruction tuning stage. Remember, we construct a large, diverse instruction tuning data set before, and we are going to use this data set and train the entire LLM and the projector on the instruction following data we constructed before. And by doing that, the model is able to generalize to complete on, say, new tasks in the wild. So this is one classic example that GPT-4 paper have used. Now I think this image is famous. This is called extreme eye rolling. And the question is, what is unusual in this image? And so we see that a man is doing eye rolling. Eye rolling is typically an indoor activity, but now the man is doing it on a moving taxi, which is unusual. We see Llama is able to replicate this example for the first time in the GPT-4 paper. And with Llama, you can also ask more questions by interacting with the demo. So after building Llama, we try to test the model and observe that there are several interesting emerging capabilities. And in this presentation, I will only highlight one interesting emerging capability, which is a strong OCR ability. Let's review the data that we have used to train the first version of Llama. It's a subset of CC3 media and the instruction tuning data that we have constructed, right? And note that there is no OCR data at all in the Llama training stage. But we see in the inference stage, the model has decent OCR capability. This is the one example. This is a CVPR logo last year. And we upload the image and ask who will be interested in the content of this image. And we see that model answers there are two groups of people who might be interested. One is the people who are working on AI and applications just like us. And there's another group of people and who are living in Vancouver, Canada, just because the model recognizes the words. A second example is saving about the logo. And we see the model is able to capture the entire phrase, computer vision in the wild. Last example is an example that I wrote in the evening we released Llama. And so we see that model is also able to recognize a new word, for example, Llama itself. So it is now known that topics like LMM was quite popular last year, right? This is all because GPT-4 shows the beginning of computer vision about, and mini GPT-4 and the Llama provided the opportunity to build such models using open source data and models. And it becomes the beginning of this research topic. It becomes quite popular. This is just the plot that I showed before the last year's CVPR. And if you imagine for this year, there are too many papers and research projects that I'm not able to put them in this plot. Okay, and so there are many new projects that have been developed in the community in the last 1 year. And as a team, as a community, and we are also actively developing Llama for new variants. And now I'm visualize the timeline for Llama development, where I also highlight some of the milestones that we have achieved in the last year. More specifically, I will categorize these research projects into three classes. The first one is trying to push the performance limit, trying to replicate GPT-4V using open source data and resources. And projects in this class include Lava 1.5, Lava Next, and the new variants. And in the second class, we are talking about applications. And for this community, we are interested in the general technology, right? But in real life scenarios, there are many vertical specific domains that people can fine tune for the improved performance. And in the last category, we are talking about the new capability. For example, how to enable image generation, how to enable visual prompting, and we can combine two-use technique with Lava to achieve such capability. But in this presentation, I will only focus on the first category, which is trying to push the performance limit using open source resources. So this is the roadmap. First talk about Lava 1.5 quickly, and then introduce some of the recent development in the category of Lava Next. Let's take a look at Lava 1.5. I will not dive into details, and there's a poster in this Friday, and you may stop by and ask him a detailed question. So the motivation to build Lava 1.5 is that when we build the first version of Lava, we mainly focus on building a chatbot where people can ask anything, the model can respond, right? And it is, mainly built for interaction with humans. But in the research community, we see that people are also interested in benchmark numbers. And so to push the performance limit for the Lava family, and we combine the academic data into the training data of the original Lava. And this is the major, modification we did to develop Lava 1.5. But this is not straightforward. And you will see that there are some conflicts if you naively combine this data. That's why we introduced some formatting prompt and trying to, guide the model to respond in a way that we want. And so by doing this, we are able to achieve state-of-the-art performance in last October on a dozen benchmarks. And at that time, the model achieved the SOTA, not only achieved the SOTA, it also, computationally efficient because we only use like 100% of the state-of-the-art model in terms of data and compute. And now let's introduce a new variant, which is Lava Next. We released it in January early this year. We combine three techniques. The first one is any resolution. So remember in the previous Lava variants, the largest resolution that we can digest is about 336, and we also observe that improving the visual representation, especially the resolution, can improve the performance. But the largest resolution that a standard VIT can digest is just 336, right? In the real world scenarios, we have images of a much higher resolution. How could we handle those images? And we propose this AnyRes technique where we divide the image into multiple patches, and then we feed each patch into a VIT, and then get a sequence of visual tokens. And eventually, we will concatenate the visual tokens together and feed them into the LLM as a visual representation. And the second technique that we propose is to further improve the data mixture for more tasks and a higher quality. And last one is as we have more compute, and now we are able to increase the size of the language model. And at that time, the best open source language model is E34B. And by combining these three techniques, let's take a look at the results. And the best model, and we see that it can it shows that some near Gemini Pro performance and on selected benchmark. Note that this is trained in 1 day on 32 GPUs. So we further scale up the language model size, and the largest language model size that we have right now is 110 billion. And surprisingly, we see that by just doing this, it's the same training recipe that we released in January. By simply replace the language model, and we see that we are able to get very similar performance with GPT-4V on selected benchmark. And if you take a look at the computational cost, it's less than 1 day with 128 GPUs, right? It means that I think, of course, in real world scenarios, there might be gaps and limitations for Llama Next, but at least it shows a recipe, right? For the community to achieve GPT-4-like capabilities. So we further, did some ablation study, and one important lesson that we learned is that a stronger LLM supercharged multimodal capability in the wild. It means that as long as we have a stronger LLM, no matter if it's stronger than capability in with a similar model size or just a larger model that give us stronger language capability. So if you have this strong LLM, then you can use the Llama Next training recipe. Then you can quickly convert this language model into the multimodal models using the recipes that we provide. So we further provided some ablation study. I'll talk about them in 3 parts. The first one is ablation study on architecture. Remember, I mentioned that in Llama, we have 2 pre-trained models. One is language model, the other one is vision encoder. Let's take a look at scaling behavior of each other. First, we use the LLM and scaling it from 0.5B all the way to 110B. And you will see that scaling up the size of LLM is very, very effective. In the second part, the other aspect, what if we're scaling up the model size of vision encoder? And turns out the scaling behavior of vision encoder is not that effective compared with the training data and the visual representation of the VIT itself. The second ablation study, visual representation, how we actually represent the image. And there are 2 aspects for us to represent an image. One is the image resolution, and the other one is the number of tokens that we could use to represent the image. We found that scaling up either of them provide improved results. And we did some detailed ablation study and provide the best configurations in the Llama Next recipe. And last part is the training strategy. When we talk about training strategy, it often includes the trainable module, which part of the model we want to train, and also include the training data, what kind of data we want to train our model. And so to summarize, we found that it is not effective to pre-train Llama model on the public data. For example, at least the original public data. For example, the well-known data sets such as COCO or CC3 media or CC12 media, right? They are probably the highest quality data in the public domain, but if you naively use this data to pre-train Llama, it won't give you great scaling performance. Instead, what we found is that we could use the previous Llama model to do captioning regeneration. And by doing that, and by using this high quality data, and by also training the entire model, not the project itself, and we found the scaling behavior is quite good. For example, we can improve the baseline results by 3.3 absolute values on several benchmarks. We also open sourced the data, the high quality data that we generated using the LLaVA model. And this is released for the COCO data set and the CC data set. And if you have used this data set before in your vision language projects, now you can consider our high quality data set version. I believe it will give you performance improvement immediately. Okay, now let's talk about video. This is the video workshop. And so remember, we use any res to represent the image, right? Which means that for an image, we will divide it into multiple smaller images. And for the LLM, it actually sees several images, right? It doesn't know it from one image or it from a video, right? This means that actually, for the image trained LLaVA model, it can directly perform tasks on video because video is essentially a sequence of image frames, right? Okay, this is the intuition that we used. So I will show you later, we can directly use this image trained LLaVA to perform our video tasks. If you really do it, we will notice that typically the sync length is not enough, right? So in the training, we typically have a limitation in terms of the sync length, which is typically 4K. But in real life scenarios, we may have videos of longer thing, with much more frames, right? So we can leverage the technique called length generalization, where we play with the positional embedding, which allow us to deal with longer videos. And lastly, we're also trying to apply the DPO technique to improve the video tasks, not SFT, but DPO. And we have some lessons. We found that the SFT data for video is not that great in the open domain, but instead we found the DPO data is great if you train the model. Okay, let's take a look at the results on the video tasks. So first, let's take a look at the results on 7B model. And we see that the zero-shot result of the LLaVA next image model is better than the prior open source model that have been trained on video. This was surprising to me, right? Because our model is never trained on video, but it performs better on the models than the models that have trained on video, right? So to further improve the performance, we apply DPO and we see further performance improvement. So we further scale up the language model size to 34B, and by doing so, we see that the LLaVA next video model is able to catch up the Gemini versions on selected benchmark. So video MME is a benchmark that was released a couple of weeks ago. And by the time it was released, this showed that LLaVA next video is a state-of-the-art open source model at that time. But yesterday, when I checked out Twitter, I noticed that it is not the SOTA anymore. A new model called Vina becomes the SOTA. Yeah, this also reflects how fast this community is, right? I also want to give you one example how the LLaVA next video model is able to do detailed captioning, because this is the one important property for vision models, especially for people who want to build the video generation models. We also developed a new variant. We call it LLaVA next interleave, and so we note that interleave is actually a general format where you can you can use it to unify many different scenarios. For example, the multi-image scenario. And in the GitHub issue of LLaVA, we noticed that there are several GitHub issues that mention that is LLaVA able to deal with the multi-image. Now I can confidently tell you yes, because of this version. We also say include more scenarios, including 3D and video and single image. Just if you consider the video setup, it's very similar setup to the LLaVA next video setup that I mentioned earlier. And for the single image setting, it's just because one single image can be represented using multiple smaller images. We put all this data together. And this comes to the M4 instruction tuning data, and we will release the data, the training data very soon. And we also develop a multi-image evaluation set. Let's take a look at the result. First of all, on the multi-image evaluation results, and we see that our model provide better performance than the previous data called the Matisse model. And on the video benchmark, the new model also outperformed the Lava Next video model that I introduced earlier. And we also included the evaluation on 3D, and it shows that this representation of 3D is better than the previous point or other representations. There's some interesting emerging capability if you put multiple different task scenarios together and train one model, which is cross-task transfer. And so remember, in the training data set, we have the multi-image scenario where we ask the difference between images. And we also have the training data. We ask the model to describe the video, the single video with details, right? And we never have a task called, tell the difference between the two videos. Now we see that with task composition, the model is able to, emerge some new capability. For example, spot the difference in two videos. So this is just I just want to highlight the block series that we have developed for Lava Next. And if you are interested, please feel free to check out the link. And we will continue release more insights and models in this blog link. And lastly, I want to highlight the evaluation toolkit that we have been used to develop the Lava variants, and which is called the LMM evals. So this is now open source, and it allows us to evaluate any model on 50 or more tasks now on different benchmarks. It supports image and video tasks. This is the last slide, and if you are interested in the basics or the advances of LMM, please feel free to check out this survey. And it's including, the very basics, for example, how to build a VIT. And it also includes some of the advances, for example, how you actually build the Lava from 1.0 all the way to the recent Lavas. Thank you.
Thanks for this great talk. So we'll now move on to the Q&A session, and if you have any questions, just raise your hand. So I wonder how was the DPO data created? So you mentioned the DPO data is much better than SFT data. So what's the difference?
Oh, okay. So let's first a great question. Yeah. So let's first talk about SFT data. So I think in the past 1 year, the video community, trying to replicate the self-instructor framework in the image domain and come up with their video instruction tuning data using ChatGPT or even GPT-4. But when we actually use the data for training, we found that if you simply train the image model directly on video, the performance will drop if you directly evaluate the results. That's why we come up to the conclusion that the video SFT data is not great. And that's why we also want to improve the data. And in terms of DPO data, and I'm not sure I have the details on this slide deck. Okay, right here. It's DPO, but it's important that how we actually collect the feedback data, right? And typically this feedback data is collected by humans. And in this work, we are not collecting feedback data from human. Instead, we are collecting feedback data from ChatGPT. And remember, I guess most of you know that ChatGPT is also great when you use it for evaluation, where you can ask ChatGPT to provide a score from 0 to 10 for any answer you provided to a specific question, right? So this also, the score that we are used to read the response for a video question answering setup. And for example, for video, and we have like 6 responses, and then we provide ask ChatGPT to provide responses from 1 to 5, and we only select the most confident pairs. And it means that for scores that are similar, we will not use this sample. And only when there's a large gap when rating these responses, we will use this pairwise data for DPO. GPT, right?
I was impressed by your questions and spending anything for there. And I was wondering if it's necessary to design a new
Right. We can see that there's a gap. We haven't found the success recipe to scaling up VIT for this setup, right? The LMM setup. I don't have a great answer. And you are asking the possibility to design architecture for VIT. My observation is that architecture might not be very important. I found that there are 2 other factors that are more important for the VIT scaling. The first one is the pre-training data quality itself. And second one is how we represent the image. For example, the resolution that the VIT can take and the number of tokens the VIT can output. Pre-training click data. If you look at this table, right, and there is one model, one VIT that outperforms them by a large margin, which is single loop. And if you take a look at the training data amount, which is 10 billion, right, which is much bigger than other VITs. And I was also told that the quality of this 10 billion data is better than the public image test pairs. Thank you.
You mean quality the data or the quality of the distribution of the data, the diversity of the data that drives like this? Because I had some chance to look at the data or see the data. They are not bad quality, but it's not bad. So how much is this data of the quality of the data important?
I see. So depends on which part of the which training stage, on which training stage we are talking about the data quality. I think right now we are mainly talking about the data quality in the pre-training stage, right? Not the alignment stage. So this is one example. So you are talking about the CC3 media, right? And the last row right there. And you can see this is one image from CC3 media. And on the right row, column, we show the original caption for this image, which is, a city of cell property, which is very short. It can mean anything, right? And it doesn't really describe the content of this image. And instead, we provide the high quality caption generated by the Llama model. You can see that it's, first of all, it's very long. And if you look at details, it actually describes many details of the patches of the image. I believe it shows you some concept that the caption quality is very, very important when we talk about data quality. And I guess you are also talking about the image quality itself, right? I don't have much experience about the image quality itself. If I want to say something, I want to say that image resolution is important, and also the diversity of the image is important. But really, in the public domain, we don't have the luxury to talk about the diversity of image because we only have a layout data set that is publicly available. And now I see that people are gradually, release a large and diverse image data set. But even when these data sets are released, I don't think most labs have the luxury to train on this data set. So I don't have much to share. Thank you.
Just for us, is there a way? Because I see the
Mm-hmm.
but it might be
Mm-hmm. Oh, this is an open research question, how to evaluate the quality of the detailed caption, right? I think there might be some recent research about it. I haven't checked the detail yet. I think there are two aspects that we want to consider. One is precision, the other one is recall. This is very obvious because I think this is also, how we actually evaluate the hallucination of the image detailed captioning, right? Like given the number of objects in the image, we can provide a ground truth, and we can evaluate, how many objects are actually presented in the caption, and right, and also the recall and precision. Yeah.
So our question about the model architecture. So as there is a particular situation in the text. So I see with the console that there are people and people. How do you know what they are doing? Another also how do you see that? So now it's very well. And the question is that is there any also another method you have tried like the selection?
Yeah, you are talking about the collection, the model architecture design of the collection module between vision and language. So in the first version, we use a linear matrix, and in Llama 1.5, and we improved it to a 2-layer MLP, right? And with 3-layer MLP, you can get a performance improvement just a little bit. And if you replace it with transformers, no matter it's 1-layer or 2-layer, and if you still use the same training data set, you will observe performance drop. So I think to answer your question, to me, the model design of the connection module is not that important. I think it is a trade-off of the number of trainable parameters and the amount of data you have to train this module well. So in reality, you can use a more complex design for this alignment module, for example, cross-citation, right? Or the design that have been used in Flamingo, which, has a lot of trainable parameter, right? But it also means that you need, train them well from scratch. And in the Llama recipe, we have limited resource. Therefore, we can only train with a small number of image test pairs. And we know that we can train it well. And with this, trainable module of a smaller number of parameters. But if you talk about the design in Flamingo, there are billions, there are over 1 billion trainable parameter. I don't think you are able to train it well with such a small amount of data.
Great talk. I wanted to know basically how you can make a conclusion about going with image models versus doing like the text training. You maybe talk about like more in terms of like what to try in terms of capturing there to evaluate those methods versus the different results between basically image text and on the video.
Oh, sorry, I don't quite get the second part of the question.
So in your experience from your talk, I think you think that using computer image text backbone is providing better results than doing video text tweaking.
Mhm.
I was wondering what you tried in the video text tweaking domain.
No. So the only thing that we try in is to pick up the image lava after instruction tuning, and then we continue train it, sorry, to the video asset data, and we observe performance drop. And we never try to use the video text pair for pre-training stage, and then for video SFT. We have not tried it.
Thank you for your awesome talk. I also have a question about the video encoder. For now, we usually extend LLM multimodal LLM by encoding the image or video into the visual space and then into the LLM. Then we fine-tune everything except to return the visual encoder. So my question is if you do you think the visual encoder would be a bottleneck for the further improvements on the performance? Because for example, visual multimodal LLM is not good at counting. It's very I just suspect that the reason could be that the embedding of one alpha and two alphas are very similar, so the LLM only look at the image to use the visual encoder, so it cannot count how many alphas there are in the image. What do you think about this problem?
Yeah, first of all, I agree with you that counting is a not well solved problem for Lava and even for GPT-4o, as I observed. It's an open question, and I think most companies, they are busy with deal with the coarse grade vision tasks. They haven't had the bandwidth to dive into the fine grade vision task yet. And answering the question, how important the vision encoder is to solve the counting problem, right? I think there are two factors that might be important. The first one is high resolution image, how to encode the high resolution image, right? And this is also true for segmentation and object detection, right? And for this traditional task, we always observe that high resolution yield a better performance for detection and segmentation. I believe it is also true for LMM, but this is underexplored. And second one is the feature encoding. And right now we are using Clip, and the Clip mostly only extract the image level features. And when we talk about the fine-grained features, especially for counting or location, if we use pre-trained Clip, this information might have lost, and that's why we need to retrain or refine the Clip so that we can get this information back.
So I have a follow-up question with the connection module design. So I wonder if it is possible to design a better interaction mechanism between the visual encoder and the language model so that the information flow can be bidirectional instead of unidirectional from the visual encoder to the language model. So I think currently maybe a major bottleneck is that the Clip visual encoder can only output a bottleneck feature, but cannot represent too much information.
Oh, I see. Right. Right. I think there are some immediate fixes that we can try. And first one is not only use the top layer features just as we did, and we can also use the pyramid feature just as we did for object detection segmentation. And I believe the performance can be improved. And but when if we you also mentioned, I think your question is about the model design for the collection module. I think one immediate thing that we can do is right now, even on the vision sequence, and it is auto-regressive design, right? And it's single directional, and we can quickly try some bidirectional interaction just on the vision sequence, right? And I guess it provides some small improvement, I guess. And if you are talking about a more advanced or more complex design about the collection module, I don't have much insights about this. And my personal feeling is the performance improvement is little.
Okay, so I think I will ask the final question. I do know that Lava has achieved very great performance on many different tasks, but still it's just on a selected set of tasks, not all of them. I'm wondering what's your vision on like further improvement of Lava to really have similar performance as Gemini or before on all of us. I mean, like other than just the scaling of the broadcast or the training data, if there's another direction to fix.
Yeah. This is a great question. I think this is great, especially for this CVPR community. I noticed that there's a gap when we develop models in a company and when we develop the models for scientific curiosity. And right now, to me, that the training recipe to develop LLM is converging. They are very similar. And I don't think there's, to me personally, I don't think there's much scientific value or curiosity by continue following the current recipe. But I think if I want to continue doing this for just the academic purpose, I would just try to pursue some less explored problem in this recipe. For example, how to enable new capabilities. For example, VidEo is just I think is an open question, and let me share more details. I showed that the image model can provide great performance on VidEo, right? But meanwhile, I want to clarify that this doesn't mean that we solve the problem. It just means that we haven't found the right problem for VidEo. And so many unique problems for VidEo, and we don't have the benchmark. And that's why we never evaluate on them. And I think this is a great opportunity, to build VidEo specific or VidEo unique scenarios and benchmarks. And after those scenarios are built, and then you will see that it will encourage new models that are trying to solve this problem. And this is the one thing. And the other one is about modeling, right? And for example, we are often talking about the unification of understanding and generation. And we do have some papers, but to me that they just show some ideas and show it works to some degree. We don't have the great model that can perform surprisingly well on both tasks. I think there is still, a space trying to, fill this gap. Thank you.
Thanks, Tom.